Hey, welcome to my 2 a.m. programming video written by a scrubby developer like me. Today we're going to be covering some pitfalls of AI and sensing with line of sight. So, in the past I'd made a pretty significant mistake that's kind of easy to overlook, but once you start to dig into the intricacies of it, you start to see kind of the limitations. So, to give you an example of what I was initially doing, you have this uh, scary looking dude over here who's like your zombie, and he sees some brains over here, this purple stuff over here. So, normally, what you would do is you take their line of sight from their eye and you look at whatever object you want, and then you figure out if they can see it or not based off of their line of sight. So normally when you have a line of sight, uh, you have a forward-looking vector, which is the direction that you're looking, and then you've got your peripheral vision off to the left and the right. And you'll always be looking at whatever's in your forward view, but you can see stuff out of the corner of your eye. So with a character like a zombie, uh, you might be looking at one thing, but the object that you might actually be interested in might be over here to the left or the right. So the initial intuition is to take that line of sight and create like a vision cone. And this is where you run into a mistake, because if you think of this as a cone, you start to run into some actual problems. So if we draw a cone like this from this line of sight, like so, and you can think of this as a three-dimensional cone in 3D space, your cone is going to have a maximum distance that you can see as well. And this is probably something that you often want to simulate, because if a zombie can see for 1,000,000 miles, he's going to see all sorts of wonderful targets that he wants to respond to. Lots of moving brains, and he's not going to be able to decide which one to go and eat. Uh, if you have a really foggy day and the player's visibility or an AI's visibility is limited by that fog, then you might want to do a simulation of the view distance. So this view distance vector is not going to be an infinite vector that goes off and sees everything that they can. So if our zombie has this vision cone, then it might initially look kind of correct, and this is kind of the assumption that I went with for a long time. So I'll show you a really quick demonstration of my zombie. So he's going to be coming out of the ground here, and he's got these various balls, which are different sorts of visual stimuli. And let's just play this and I'll show you. And you can see that cone thing that's attached to his face. And as he moves his head, you can see that the things that you can see varies based off of whether or not something is inside of that cone, right? So as the zombie is in kind of like this idle pose, the vision cone kind of like goes up and down and around, and you can also have like some animation that makes him turn his head to look around and look for different targets. And the idea is that if something's inside of this cone, then he can see it. But what happens if we say, well, this zombie's vision is, let's say, 100 meters, and we just move something just barely outside of his view range. And let's say we repeat the same thing for this guy over here, and maybe this guy. And let's just see if I approximated that about right. Okay, he's gonna pop out of the ground. And now he's going around looking for stuff. I just barely missed putting it out of too far of his range. But you start to run into a problem here. Let's say our zombie's current line of sight is 45 degrees, and we're like, well, you know what? I want to increase his field of view to 90 degrees, because like, if you're actually a human and take your left and right hand and put them as far away to the left and right as you can, until you just can barely see each hand and measure that angle, it's like a 90-degree angle from your forward vector to the sides. And if your zombie has decent peripheral vision, or other character has good peripheral vision, then you want to say, I want to have that 90-degree peripheral vision. But now, if we're representing that with a cone has a base length, and then it has that half angle. But if we increase our view angle to 90 degrees on each side, then how do you represent that with a cone? And if you want to change like the view distance, say to like a 1,000 meters, then what kind of cone would you have? You'd have some cone that's like super wide, and if it goes out to 1,000 meters in the forward direction, you're going to have a lot of craziness off to the left and the right. So let's just redraw this just to illustrate. We're gonna let's just get rid of all this stuff. So if we had our forward vector, and let's say we don't want to change the distance, let's say it looks like this, and let's just have a really extreme example. We've got the base of the cone, something like this, and then if you wanted to have that 90-degree field of view, you'd have to go something like this and like this. But the problem is, if this is your distance that you can see, then you're going to start having like a whole bunch of dead space and false positives. So if the farthest that you can see is, say, 1,000 meters or even 100 meters or whatever you want, then out of your peripheral vision, because we're trying to create this cone, like this region up here, let's see if I can color it blue. Oops. These regions are going to be giving you some really serious false positives, like your line of sight to, or your view distance to the left and the right is going to be extreme. And if you wanted to like see a million miles, all you do is turn your head a little bit and then look out of the side, and then you'd be able to see whatever you're looking for. So obviously that's not going to work. So what is the solution to this? Well, the solution is to actually stop thinking about cones and instead start thinking in conic sections of a sphere. And I think there is there's a conic sector, which is kind of like this mathematical type of object that is much better at representing this. So I created a custom shape inside of Unreal Engine that looks kind of like this, which is a much better approximation of your view region. So you can specify the radius, which is the furthest that you can see, so you can boost that way out if you'd like, or shorten it up, doesn't matter. But as you increase the radius, all that does is it increases the distance that you can see, but it does not change your left and right view angle. Alternatively, you can change the view angle and it's not going to change the radius, which means that by changing the distance that you can see to the left and right, you're not going to be creating all that extra dead space that gives you false positives. So your view distance is always going to be the same regardless of what radius you use. And the way to think about this is actually just a part of a sphere, and you can actually go all the way around to 180 degrees, which creates an actual sphere. And now you can move that around. So a sphere is just the parent shape of some sort of a vision cone. Now you sometimes might want to have like something that's a little bit more than a hemisphere. Maybe you have some sort of an herbivore type of creature that has eyes on both sides of the head with a very large, not like a fisheye lens type of a thing that can see more than 180 degrees, and then you could do this. Or perhaps you might have a different type of a sense, such as hearing, where maybe you want to simulate something like this, where this is one ear on the side of a skull, and this area of the dead space is actually just blocked by the skull itself, and you can't hear very well. But maybe if you have two ears, then you can simulate that much better. So this is definitely a much better way to sense whether something is inside of your sensory range. So when I was developing this, I thought it was also really important to make sure that this actually works really well and can detect whether or not something is inside of it or outside of it. So I created like this unit test that goes through and tests out all the different values that you could potentially test. And it's kind of a rigorous test, and here's kind of what it looks like. Let's go and look at this from the top down so that it makes a lot more sense. So here's our vision cone right here, and then here's a whole bunch of different spheres that we might want to test for overlap or containment or collision with, and these spheres might be objects that we're trying to sense. And I also have a way to test whether there's a point inside of this. So it's super important to do these auto tests, not auto tests, but just rigorous unit tests in order to find edge cases. So let me give you a demonstration on what this looks like. We have a sector that's spinning around at a certain rate, and each of those red points are points that we're testing for containment within our sector, and if it's green, then it's inside of it. If it's red, then it's not. And we've also got these spheres where if they are overlapping our sector, then they turn green. And as you can probably see here, we've got a couple red dots just on the very edge that stay red even though our sector is overlapping them. And the reason for that is because there's floating point precision errors happening where I'm computing each point with cosine theta, sine theta, and affixing a radius of exactly 100, and our sector has an exact radius of 100, but there's going to be some very small noise which causes some of them to not actually work. So to fix that, all you have to do is go into your sector and set the radius to like 100. So I accidentally had my obs turning off after I hit the period button, so as soon as I did 100.1 it turned off my recording, and that was a mistake which I will have to fix later. Anyway, we changed our radius to 100.1, and then as you can see that got changed to 100.0999998, and that's the floating point precision noise that I was just talking about. So when we hit play, you can see that we are just barely inside now, and all the dots turn red, as we would hope. So one super important part about this testing is that this helps you identify problems inside of your implementation. And one problem I found was that when I took this sector and I rotated it to something like 33.1 degrees. Let's do that here, 33.1. I'm not going to stop our recording this time. For some reason, this was registering as no longer intersecting with this circle, but you can obviously see that this whole entire region of the sector was still overlapping. So it very briefly blinked off and on, and that blink was actually an edge case bug that I had not really considered. And it is literally an edge case because the way I was computing whether this was inside or overlapping with this circle was by taking a line from the center of this circle and drawing it all the way here, and then finding that point and then testing whether that point was inside of this geometry or not. And when this is right on the very edge and you try to draw a line all the way up to the maximum radius of the circle, it's literally on the edge. So you got that edge case. So if this was here, it would very easily be registered inside that shape, but if it's like just at that edge right there, then it would be an error. So after lots of testing, I was able to find a flaw in my implementation, and I found that if I only test for this condition, I actually also needed to test a condition for the line from the center of this circle all the way to the edge over here and see if this was intersecting with this shape. So it would be testing for this point as well as this edge point. And if one or the other is true, then you know that you're still overlapping with this shape. So that's truly the value of rigorous testing, is to find these edge cases before you start using that out in the wild. If I assumed that this worked without testing for that edge case, I would have had like success for 98% of the use cases in production, but that last 2% would be something that would cause a lot of headache further down the road as you're figuring out, why is my zombie not seeing something when clearly his vision cone is intersecting with the object that he's supposed to be seeing. So it was obviously this edge case. So as far as the implementation of this goes, I discovered that this line drawing code needs to be done on the engine side, and you can't just do that in a plugin. So to do that, what you do is you create a new component and you put it into the components section of the engine code in the same spot that you have your sphere components and box components and other stuff like that. And for some reason that gives you access to engine stuff due to this engine API markup tag here. So as far as the implementation of that line drawing stuff, you use this primitive scene proxy, and inside of there you can call this PDI draw line or draw circle, and that allows you to render lines and circles using the GPU, and it goes much faster than the debug draw line, so you get much better performance, and you also don't have to specify a timeout and continuously flush your lines, as you can see from my demo in UE4. So if you're curious on how the math for that sector goes, you're free to pause the video and look at all this code. I'm not going to go through it and explain it line by line, but if you'd like, you can study it. I'm not guaranteeing that it's perfect, and I might make some changes later on down the road as I find more edge cases or areas that I can improve it, but I think it's pretty decent, so go ahead and copy that onto your own computer if you'd like. I won't be publishing this or anything, so The other two pieces of code that are going to be super interesting and important are to test whether a sector component contains a point, and here's the code for that. You can pause and look at that. And then here is the code to test whether it overlaps a sphere. This is this last piece is something that I discovered from my testing, and these two bits of code took me maybe like an hour or two to write. If you're interested in the sector component header file, this is what it looks like. I have a sector struct, which looks like this, where you pretty much specify a position, a radius for your sector, a rotation for your conic section, your half angle, and then here's a bunch of boilerplate code for the sector structure. And then here is my new sector component, which inherits from the shape component, and I expose the radius and half angle to protected classes on the blueprint side, and most of this stuff is just copied straight over from the sphere component. As you saw, spheres are a superset of a sector. And that's pretty much it. So, in summary, sectors are much better to use for sensing things than a cone, because you can change the view angle of a sector without having extra dead space on the extreme edges, and you can go more than 180 degrees on your left and right. So I think this is far superior to the naive approach. Anyway, that's it, and thank you for watching.